Computing the 34th Fibonacci number with the naive recursive function from last video takes over 11 million function calls, and a noticeable pause before the answer appears. In this video, we add one dictionary to that function and cut those 11 million calls down to 65. The technique is called memoization, and its whole idea is to never compute the same value twice. The trace of Fibonacci of 6 exposes the problem. The same values get recomputed again and again. The fix is to stop redoing work we have already done. We want a data structure that lets us keep track of values as we calculate them and look them up later. A structure that maps one thing to another. Anytime you hear keep track of and look up, a little bell should ring that says dictionary. So the memo is a dictionary. Each key is an input n, and its value is Fibonacci of n. And it starts live with the two original base cases already loaded, one maps to one and the two maps to one. Here is the function. Fib efficient still takes n, but it now takes a second parameter as well, a dictionary d passed in with the base cases already inside. The first thing the function does is check whether n is already a key in that dictionary. If it is, it returns the value stored under n and makes no recursive call at all. That check is the new base case. Nowhere in the code do we say Fibonacci of 1 is 1 and the Fibonacci of 2 is 1. Those two facts live in the dictionary itself. If n is not in the dictionary, we compute it. We make the same two recursive calls as before on n-1 and on n-2, but instead of returning their sum right off the bat, we save it in a variable, which is perfectly legal. Then comes the key move. Before returning, a straight dictionary assignment stores the result under key n. Only then do we return the value, passing it back up the chain of calls as usual. Compute once, store, then return. Watch it run on Fibonacci of 6. We initialize the dictionary with 1 maps to 1 and 2 maps to 1 and call fib efficient of 6. 6 is not a key, so we recurse and the same left-hand descent happens as before. Nothing is stored for 5, so we explore it. Nothing for 4, keep going. Nothing for 3, keep going. At 3, the two recursive calls finally hit the dictionary. 2 is a key, so it returns 1 immediately, and 1 is a key, so it returns 1 immediately. Now we know Fibonacci of 3 is 2, and before passing it up, we store it. Key 3, value 2. So far, this looks much like the old trace, except that we are recording as we go. Back at 4, the right-hand call asks for Fibonacci of 2. It is in the dictionary, so the sum finishes at once, and we store key 4, value 3. Back at 5, the right-hand call asks for Fibonacci of 3. Last time, this is where we re-explored a whole subtree, walking down into 2 and 1 all over again. Not now. 3 is already a key, so we return its value, 2, immediately and never walk that path. 5 finishes, and we store key 5, value 5. Finally, back at the top, 6 asks for Fibonacci of 4. The very point where last time we were nowhere near done. 4 is in the dictionary. We look up its value, 3, add it to 5, get 8, and store key 6, value 8. That is the answer, and since this is the top call, there is nowhere further to pass it. Count the work. 9 calls instead of 15 for the naive version, and the gap explodes as n grows. Every value was computed exactly once. Every repeat became a lookup. How big is the improvement at scale? Both versions are in the lecture file, so you can run this experiment yourself. The naive version, the one that stores nothing, computes Fibonacci of 34 in over 11.4 million function calls. The exact count is on screen. The memoized version produces the same answer, about 5.7 million, in exactly 65 calls. We did not go from 11 million calls down to 2 million. We went from the order of millions to the order of tens, a genuinely staggering speed up. And you can feel it. The naive version makes you wait. The efficient one is instantaneous. The enormous count makes sense. Even in the little tree for Fibonacci of 6, the naive version called Fibonacci of 3 on 3 separate occasions and Fibonacci of 4 twice. On the way to Fibonacci of 34, Fibonacci of 3 gets recomputed over 2 million times. 65 calls means something very different. 32 values from 3 up to 34, each computed exactly once. Why does the call count matter so much? Because every function call carries overhead. Python has to create a fresh environment for the call, bind the parameters inside it, run the body, and tear it all down when the call returns. Do that 11 million times, and the overhead alone becomes the whole runtime. By contrast, a dictionary lookup is essentially instantaneous. Hash the key, fetch the value, done. Memoization wins because it replaces millions of expensive function calls with a handful of nearly free lookups. There is a trade-off here, and it is worth naming. We bought that speed with memory. By the time Fibonacci of 34 finishes, the dictionary holds 34 entries, the 2 preloaded base cases plus the 32 values computed along the way. 34 entries is nothing, but some programs run where memory is genuinely scarce, and there you might make the opposite choice, spend time recalculating rather than space remembering. That is the shape of the deal. One program stores nothing and is slow, the other stores things and is fast. When memory is cheap, and it usually is, trading space for time is one of the best bargains in programming. Memoization changes a recursive function in 3 small ways. First, the base case becomes a question: is n already in the dictionary? If so, return the stored value. Second, the recursive step computes each value once, stores it in the dictionary, and only then returns it. Third, the original base cases become nothing more than preloaded entries. Everything else about the recursion is untouched. So whenever a recursive function keeps solving the same subproblems, remember the pattern. Check the dictionary first and compute only when you must. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.